Today we are going to discuss about the module 6 of CS 305 microprocessor and microcontrollers. Today we will discuss about programmable interval timer, that is Intel 8253 or 8254. It is always possible to generate accurate time delays using the microprocessor system by using software loop programs, but that will waste the precious time of CPU. Normally, when we doing a program, we are using some delay circuit to generate the delay. So, using some loop programs. So that time delay, generating time delay is not accurate one. So we need to provide an accurate time delay. The Intel introduced a new chip that is known as 8253 or 8254, which is a hardware solution for the problem of generating accurate time delays. Using this 8253 or 54, we can generate a accurate time delays. So it's also known as programmable interval counter, and it has 6 modes of operations are there, and it has 3 independent 16-bit down counters are there. In this interval PIT, there are 3 counters are there. Each counter has 16 bits. All are independently working. And the operation is how it works. A 16-bit count is loaded on the counter, and on command it start decrements. When the count reaches 0, it generates a pulse. What are the features of 8253 or 54? The first one is it has 3 counters, and each program independently, each are 16-bit counter, and it can be programmed for either binary or BCD count. So the counters support either binary count or a BCD count. BCD means binary coded decimal count. It can handle input from DC to 10 MHz frequency. And to operate a counter, how to operate a counter? First, we need to load a count, 16-bit count in its register on command, and it begins to decrement the count until it reaches 0. At the end of the count, it generates a pulse that can be used to interrupt the CPU, and it is compatible with almost all microprocessors. Then 8254 has a powerful command called read back command, which allows the user to check the count value, the programmed mode, the current mode, and current status of the counter. So 8254 supports some additional command which is known as read back. Using this command, user can check the count value in the counter, and also which program mode is used, and current mode and current status of that counter. All these details are available from this read back command. Then architecture of a 8254. It mainly the architecture containing 3 counters, count 0, count 1, and count 2, and each has 3 symbols, 2 incoming signals and 1 outgoing signal. The outgoing signal is the output out 0 line. So here for counter 0 it is out 0, for counter 1 it is out 1, and for count 2 it is out 2. And the 2 incoming signals are, one is clock, there is clock frequency is given here, and gate 0. So in each counter there are 3 signals are there, 2 incoming signals and 1 out. There is a control word register that register containing the control word, and that control word control the all counters, and there is a read write logic signal. Read write logic unit containing 5 signals are there. One is chip select. When this chip select is low, then only this 8254 or 53 will be selected, otherwise it is not enabled, and we can't count if it is an enabled. Counting only start after the 8254 is enabled. And there is two signal A1 A0, and for read operation there is a read signal, and for write operation the write signal. A1 and A2 are used A0 and A1 are used to select the counters and the control word. And there is a data bus buffer. It is an 8-bit data bus interfaced with the external circuit, that is D7 to D0, that is the data bus. 8-bit bus is there. That bus is connected to the external device and the internal bus. Then read bus data bus buffer. It is a tri-stage bi-directional 8-bit buffer which is used to interface 8253 or 54 to the system databus. So system databus and the 8253 is interfaced through the databus buffer, and it has mainly 3 functions are there. First, programming the modes. Already told that there are 6 modes are there, so that modes are programmed by this databus buffer, and loading the count registers and reading the count value. All these are done by the databus buffer. The next one is read write logic. It consists of 5 signals: read, write, chip select, and address lines A0 and A1. So in the peripheral IO mode, read write signals are connected with IO read and IO write. We know that peripheral means is related to the input output devices. So if we want to read from an input device, we are using IO read. If we need to write to the output device, we are using the control signal IOW. If it is memory related operation or memory mapped IO, then for reading we are using memory read MEMR, and for writing we are using the command or signal MEMW, that is memory write. The address lines A0 and A1 of the CPU is connected to the address lines of A0 and A1 of the 8253 or 54, and CS, that is chip select, is decoded addresses. So the control word register and counters are selected according to the signal on the A0 and A1. Here, if A1 and A0 both are 0, then it will select the counter 0. If A1 is 0 and A0 is 1, 0, 1, then counter 1 will be selected. And A1 is 1, 0, then counter 2 will be selected. If 1, 1, both are A1 and A0 are 1, then we will select the control word register. So for selecting the counters and control word register, we are choosing the address lines A1 and A0, which is connected to the processor address lines A0 and A1. Then next is control word register. The register is accessed with when a address line A0 and A1 are at logic 1. When we know that A1 and A0 both are 1, then it will select the control word register. So it is used to write command word which specifies the counter to be used. Is mode either a read or write operation? We are using identifies using this A1, A0, read, write and chip select. If CS is equal to 0, then only we select the chip or enable the chip. Then only it performs this operation. So when A1 is A0, both are 0 means it will select the counter 0. Then if it is a read or write operation, it is determined by this signal. If write is equal to 0 and read is equal to 1 means it perform the write operation. When WR is equal to 0, then it related to the write operation. If it is 0, 1, A1 and A0, then count 1 0 means counter 2 and 1 1 means is write the control word. And if read are 0, then means it is a read related operation. So here 0 0 means counter 0 will be read, 0 1 means read from the counter 1, 1 0 means read from counter 2 and 1 1 if it is not a read command from the control word. We can only write to the control word, we can't read from the control word, so there is a no operation, the remaining are no operations. Then counter, here each counter consists of a single 16-bit counter. So each counter is a 16-bit counter. It is a down counter and it can be operated either in a binary or a BCD. Its input and outputs is configured by selection of the mode stored in the control word select read register. So control, depending upon the control word register, the input and outputs are configured. The programmer can read the content of any of the three registers without disturbing the actual counting process. Counters are programmable by writing a control word, then initialize the count. So if you want to uh, programming a counter, if you want to program a counter, then first we need to write the control word, after that we need to initialize the count. So if there is a signal called gate, that gate is equal to 1, that means it enables the count. When gate is equal to 0, then disables the counting. So when the value of a gate signal is 0, then there is no counting procedure will be take place. So only counting is take place when gate value becomes 1. This is the control word format. It is a 8-bit, so D0 to D7. So last one, BCD. If it is this value is 0, then it is a binary counter. Otherwise, it is a 1, then it is a BCD counter. Then next 3 bits D1, D2, D3 are indicate the mode operation. So there are 6 mode of operation. It starts from mode 0 to mode 5. That is determined by this 3 bits. If all are 0 means it mode 0. 0 0 1 means mode 1. Don't care, 1 0 means mode 2. And 1 0 0 means mode 4. 1 0 1 means mode 5, like that. The next 2 bits are read write. Here 0 1 indicate that it is a read write least significant byte only. So it is a 16 bit. It is a 16 bit. So in this 16 bit only we are selecting the least significant bit. If 1 0, then it is a read write most significant byte only. If 1 1, we can read at least significant byte first, then most significant byte. Then how the read operation, how many bytes can be read, or that will be determined by this bit. If it is 0 1, then we can only read the least significant bytes, and not LSB is bytes, 8 bits, and 10 indicate is can read most significant bytes, and 11 means first we can read least significant bits, then next most significant bytes can be read. Then select counter, we this last d6 and d7 bits are used for selecting the counter. If both are 0, it select the counter 0, 0 1 it indicates counter 1, and if it is 1 1 it indicates a read back command. Last class we discussed what is a read back command. This command allows the user to check the count value, programmed mode, and current status of the output page, or the current states of the counter. Then there is another command is counter latch command. It is similar to that of control word register or control word, but the two bits d5 and d4 distinguish the command from this control word. If we selected the counter latches the count at the time the counter latch command is received. So when a counter latch command is received, at that time the counter will start the selected counter latch start the count. The count is held in the latch until it read by the CPU. So latch means it's a temporary storage area. So when a command is used to write the count to that latch, then latch will store the count until it read by the CPU. Thank you.